here?
Yeah, I didn't
Right.
understand what they meant.
The first time I read that, I read it one way, and then I had to reread it again, and I did it the other way. And you're not going to like my answer, but I don't like the question now. Do you notice that I'm going through and checking every single one of these things? And the question, the way I read it, was not the way they meant it. The way I read it first was that if you choose, let's say I randomly choose female, male, male, and female, any combination of two males and females have the same probability of happening, right? So all I did is I randomly chose that one, and then I picked every other situation where there was two males and females in any order I like. But in fact, the question wasn't that. The question was equally likely events. Well, do you know that every single one of those is equally likely? That's why I've checked them all.
I thought about that, but I didn't think that they would. Okay, I didn't try checking them all because I thought that that would have been wrong, and I was on my last try.
You didn't want to use it up, right?
Yeah, because I didn't think that they would mean check all of them. Like
I think we were both, when I first read it, I thought the same thing, right? Now, just to finish this off then, since it's here, what is the probability that all 4 children are male? Well, if you look at that list, there are 16 in them, but isn't only one of those 16 everybody being a male? So that would be the answer. I think they want it as a fraction, so don't write that, by the way. Do you know that when you hit it, you have a little thing over here that you really do fractions with? You know, that little box that they have where all the little symbols are. Make sure you use that. Now, the complement of a Venn, all 4 children are male. That's dead easy. Isn't the complement, that's a fancy word for not that thing. If that thing, in this case, is all males is 1/16, isn't that complement not that thing, the other 15? So that would be the second answer. Is that what you're looking for?
yeah, thank you.
Yeah, I fell for the same trap of not reading a question really carefully. Every word's a prisoner, you know. If you don't read them carefully and interpret them, you sometimes think they're asking A when they're really asking something else, B. Okay, any other questions?
I had a question just out of curiosity of
Sure.
how, I mean, I'm sure you'll probably cover more of it tomorrow for the exam, but like roughly how big is the exam going to take? Is it going to take the full 3 hours, or is that just given set amount of time so for everybody?
Right, well, my exam will not be designed to take 3 hours. It'll be designed to take less than 3 hours, so
Okay.
that you have an opportunity to, you know, go back and do whatever you need to do.
Right.
The number of questions I can't tell you right now because I haven't made it. I wait until the weekend when my brain is rested, because that's a pretty big thing. But one of the cool things that WebAssign does for me is when I choose a question, it also tells me how many minutes people in the past who've done the same question have taken. And so
nice.
when I pick the questions, it will tell me for these 15 questions, 150 minutes was how many minutes the average student took. So that's kind of what my goal will be, to pick enough questions that last roughly about 2.5 hours. That way I've got a wiggle room of an extra half hour, so that if you're a little bit slower, you think about things a little bit longer, you still have time. And once the test is over, because it's a time test, right? So you start it at, let's say, 9 and you finish at 12. For some reason, that seems to me to be the number that I think I've written down somewhere, 9 till 12. It won't appear on WebAssign until 9, so you have to kind of wait until 1 minute past 9 and go in. And at the end of 12, it will cut itself out. It will just lock you out. So whatever answers you've done, that's as good as it gets. And I then give you 1 more hour, which we'll talk about tomorrow, to take copies of your written work, because that's really how I'm going to be grading your midterm, on the written responses. And how to take those, turn them into a PDF using a piece of software, a little app that you take a picture of it. It turns it into a PDF, and then you'll upload it to Canvas. And we'll talk about that tomorrow as well. And that's kind of how it'll work. And you've got 1 hour from the test finishing to you getting that PDF into Canvas.
Awesome.
Right, so that's kind of how it is. But how many? I don't know.
We're
Um,
uploading on Canvas and not WebAssign?
the thing is in WebAssign. The questions are in WebAssign, just like your homework assignments. Canvas is used only to upload the PDF of your work in. Does that make sense?
Yeah, makes
And you
sense.
said we can just do it on, like, if we don't have access to a printer, we can just do it on regular scratch paper and upload the scratch paper, right?
Actually, when you're doing your work in, I would do it in paper because typing it would take forever. Right.
Well,
So
yeah,
just write.
no,
Yeah.
like we
question.
can just use regular blank scratch paper, right? We don't
Yeah.
have to have a printed copy. Okay.
Yeah, you don't need to print the test out. You just need to
Okay.
write the answer. I would make my life easy. Will you make sure it's called 1, 2, 3? Because sometimes the questions blend and I don't know which one it is. But I mean, apart from that, square paper, line paper, whatever suits you will work fine.
Perfect. Thank you.
Okay. Now, I know that you're probably interested in more questions, but maybe we could keep these till tomorrow. That way, I will have more information, and hopefully you will ask me some cool stuff that I'll have forgotten to tell you, and I'll chuck that in as well. Right, so right now we are about to start our next section, which I believe is section 6.1. Let me check in my gizmo. I know what it's about, I just can't remember its number. 6.1. So today, 6.1, we'll get that finished before the end of today. We'll get started 6.2 today, and we'll finish 6.2 tomorrow, and hopefully have some time left to talk about what the test is going to look like and the midterm test. And if we have any time after that, we can even say, can we go over this topic from chapter 2 or something? We might have a little bit of time. I'm not sure how much. So let's start with, imagine I have a population, right? A whole load of people. And this is what their graph looks like. Basically, that's histograms, but you know we draw them. What name do we give to that kind of shape?
Symmetrical?
Yeah, I would use the word symmetric, which it certainly is. If you go looking online, you'll find that it's also called a bell-shaped curve. It kind of looks like an old-fashioned bell, doesn't it? And it's also called, I think in this textbook, you tell me if I'm wrong, is it called mound-shaped or something like that?
Yes.
Yeah, I don't like that term, but we have to use it because they're going to use it in the questions, right? So you have to know what they mean. This shape is mound-shaped, it's bell-shaped, it's symmetric. We are going to be working with population distributions, right? So that's everybody in the entire population, right? Where the data looks like that. Lots of things have distributions like that. Imagine it was a test. So the population would be everybody in the class, right? Just based on this number, and since it's a population, I'm going to be using mu rather than x bar. Remember, mu just means the population mean, right? It's just the same thing as a mean, right? Would you agree that in this picture, that when you are mound shaped, isn't the place where the hill is going to be the mean? Agreed?
Yeah.
That's where the mean is. So if somebody gives you a picture like that and they put a 70 here, couldn't they ask you, what is the mean of this population? And you're going to say mu equals 70, right? The mean is 70, and it will be.
Oh, I thought that was the median.
It is, but isn't it both? Because it's
Huh?
symmetric. Yes,
Oh, okay, that's right.
right? By the way, in chapter 6, the median doesn't exist. We pretend it's not there. We are only going to be using the other two guys, the mean and a second guy who uses this weird letter of the alphabet. Does anybody remember what the Greek letter that looks like an O with a little hat on?
Is it sigma?
You nailed it. And let's say sigma is 5. What does sigma represent? The population?
Is it the standard deviation for the population, or is it
Yes,
for the
it's
sample?
right.
Oh,
Stop there. You got it the first time.
okay.
It's the population standard deviation. So for this population, the mean is 70. That you can tell. It's kind of hard to tell what the standard deviation is for a picture, but let me show you that for these particular diagrams, which are called in almost every textbook I've ever seen, it's called a normal distribution. It ends up looking like this. You take the mean. If the standard deviation is 5, then this guy is 75, this guy is 80, and this guy is 85. And if you go back, this guy is 65, this guy will be 60, and this guy will be 50. And technically speaking, these population things do tend to curve a little bit longer, but the majority of populations that are normally distributed, right, things that are bell-shaped like this, the mean is always in the center. And have you noticed that if you go 1, 2, 3, and 1, 2, 3, you're pretty much going to have every single person in that population included in that. And do you notice that from here to here is 1 standard deviation, that's 2, and that's 3. So you will see a general picture that looks something like this. Right in the middle is mu. And then this guy is mu plus a standard deviation. This guy is mu plus 2 standard deviations. And this guy here is mu plus 3 standard deviations. And then if you go backwards, you get mu, take away 1, mu, take away 2, and mu, take away 3. That is pretty much every normal distribution in the universe now. Which means if I gave you a picture and no other information except what you see on the picture, and I tell you this is 80, that this is 90, that this is 100, and this is 110. And if I go back the way, it would go 70, 60, and 50. And I said, using this picture, can you tell me what the population mean would be and what the population standard deviation would be? And the answer is yes, you should be able to do so. Would you agree that the mean is right in the middle, in this case 80? Now, based on the way that these have been built, do you see they've been built in little chunks of, what in this case 10? Doesn't that tell me that the standard deviation would be 10? Now, it's interesting to say that every single distribution that is basically symmetric like this one, that this is what the shape of it looks like, right? Starts high and drifts away. Now, imagine I gave you no information at all, except 2 pictures. Which one of these 2 populations, and we'll assume that these scales here, although you don't know what the numbers are, right, are the same scale, right? Which one of these 2 has the biggest standard deviation?
The second one?
Yeah. How can you tell? Well, would you agree that if you go one either side, isn't that, well, let's do it in the big picture, isn't that much bigger than that? That's the easiest way, right? So if you have a bell-shaped curve, a mountain-shaped curve, I'm trying to use every version of the terms that you can think of, a normal distribution, it has a very, very structured shape to it. The mean is always in the center. And if you go 1, 2, 3 either side, the gap between the 1, 2, and the 3, in this case it's 10, will be the standard deviation of that particular population. So if I have a population that's that shape, don't I only need to know the mean and standard deviation to kind of know pretty much everything I need to know about it? I don't need to know the 365 million Americans if you tell me that picture. I get just as much information from that. Now, there's even more information, and this is phenomenal. The guy who figured this out, and I use the term guy to mean girl or boy. To me, guy is genetic now, right? Because it's just as likely to have been a woman as a man. Here is a normal distribution, right down the center. We'll call this guy 100, so it might be IQs, right? If you go 1 standard deviation either side, let's say that's 110 and that's 90. This is called mu. This is mu plus 1 standard deviation. This is mu take away 1 standard deviation. And we are focused on only this piece of the curve. We describe this as being 1 standard deviation from the mean. So can you imagine you got the IQs of every American. The average IQ is 100, the standard deviation is 10, so you get a picture that looks like this. Now, you know that there's a second guy and a third guy. I just haven't put them in because they're a distraction, right? You always get the guy in the middle, 3 to the left, the guy in the middle, the same 3 to the right, right? The standard deviation is you like counting. Do you know that the number, the percentage of the population that lies between 1 standard deviation either side of the mean is, give or take a little, the same number every time? And that magic number is 68%. So, for example, suppose I know that the mean of a test was 70 and that the standard deviation was 5. If you take 1 standard deviation, right, either side of the mean, do you see that you get scores between 65 and 75? I can tell you that 68% of the class got a score in this test between 65 and 75. That's kind of cool. Now, I'll talk a little bit later about what about 2 standard deviations away from the mean? And is there a rule for that? Yes, there is. And how about, finally, 3 standard deviations away from the mean? Is there a rule for that? And yes, there is, but let's focus on this one. Now, let's pretend, just for a minute, that someone collected enough data that they're pretty sure that the data they've got is just as good as the population. And I'm making this up. But let's suppose it was the potassium level of a normal adult male. And very often when you do blood tests on people, you typically break them at least into 2 groups, adult males and adult females, and then you know, male childs and female children, right? And sometimes you even do older males and older females, because isn't there a variation in the potassium level for males compared to females, right? Sometimes it's to do with hormones or just the body chemistry, whatever it is. It's better to have separate figures, right? Because what might be high for a male could be quite low for a female, right? Testosterone. Guys should have a lot of that. Women do have, can't say the word, testosterone, don't you? Right? Which is why you grow moustaches when you get older, Your estrogen level reduces, but your testosterone level doesn't. And so when you put them together, that's a nasty side effect, right? A gay guy get man boobs, so we get the opposite, right? For whatever reason. For some reason, my brain's drifted a little bit. But back to the focus. Suppose that 80, whatever it is, units per cubic centimetre of potassium, that would be the typical male potassium level, right? And let's suppose, so that's 80, and let's suppose that the standard deviation was 20. Now, if you go one standard deviation either side, you get that normal. And that's 68% of the population. So when you go and get your blood test, have you ever done that? If you ever get your blood test and they give you a number and then they give you a range, and as long as you're in the range, nobody's worried about it because that's the typical range, right? That's the normal range. That could quite easily be the 68%. But you might wonder, where did that number come from? Do you know it just comes from the mean, right? The mean of the population, give or take, say, one standard deviation. That would be normal. Now, if you take the same guy, but you don't go one standard deviation away from the mean, you go 2 standard deviations. Now, can you imagine that that's going to be more people, right? It's a bigger thing. It should be bigger. Now, when it was 1 standard deviation, like here, wasn't the magic number 68% of the people will probably be in that range, right? That's where most of your numbers are, 68%. What's that, 2/3 roughly? I don't know, some of you might have read this or you just know it. 2 standard deviations is typically a fixed number for every distribution in the world. 2 standard deviations away from the mean. Anybody know what it is when I write it down?
98%?
Pretty close.
Is it 99.7% or
That's,
0.6?
oh, you are bouncing either side. 95.
Okay.
So 95% would be in that range, okay? So if I was doing the medical field, do you know I would be saying, look, if your range is 60 to 100, right, if your potassium level is 60 to 100, I'm going to call that normal. Now, when you move it up to 2, do you see that there's a little boundary here and a little boundary here? What do you think they're going to call somebody who gets a score whose potassium level is 100 to 120? Or if you go the other side, wouldn't it be the 40 to 60? So basically people who live in here, and the other group is people who live in here. Wouldn't that be considered a high potassium level? And wouldn't this other one be considered a low potassium level? Now, those are distinctly different problems, right? Certain diseases or something wrong with one of your body, your body chemistry, won't they generate high potassium levels, and other totally different diseases maybe generate lower ones. Sometimes you have glands that regulate certain chemicals in your body, and if that gland is not working, it very often shows up in certain, potassium level, iron level, oxygen level, the kind of things that you measure in the medical field. They end up being not working the way they should, and it ends up being high or low. And isn't that probably one of the first things if you're being diagnosed? I come into the hospital, I don't feel well, right? That's kind of the start. And what do? Well, they'll probably take some superficial things, not superficial, but won't they take your blood pressure, your body temperature, and your heartbeat? I'm trying to do a nurse's job. Is there anything else in there that's not like the first 3 things you do is you check those things, right? Is there a 4th thing I don't know about? Or is that typically the first 3 things you would look at? You know, what's your temperature, what's your blood pressure, and what's your heartbeat, right? Okay, I didn't miss anything. Oh, cool. Then they'd ask you symptoms, but wouldn't one of the things probably happen to you, especially if it was severe, wouldn't they take your blood pretty quickly and say, okay, I want a full spectrum analysis, or whatever they call the thing, right? Which basically they test for everything under the sun that they can think of, or at least they measure things. And back comes back, oh, your potassium level is high. Now, if you're in the medical field, which I'm not, you might say, these are the kind of diseases that make potassium levels high. And maybe you also have your iron level is low, right? Now, when you put things together, it's a bit like Sherlock Holmes, isn't it? You've got clues. And if you've got enough clues, typically one disease or one problem tends to generate this combination, and a different disease or something wrong with you does another combination. But it all starts with highs and lows, right? Unless you've got a photographic memory, aren't the doctors going to look at the report and say, oh, high potassium, low iron, whatever the other thing is, right? Cesium level, something. And then they start thinking, what kind of disease does that? And maybe that will get them closer to figuring out what's wrong with you. Now, I said there's three standard, there are three pictures, right? One standard deviation away from the mean, oops, you can't see it. One standard deviation away from the mean is 68%. Two standard deviations away from the mean is 95%. And within that, can you see how you can now figure out highs and lows? Won't the last one be 3 standard deviations? So let's try and draw my third picture. I'm trying to keep it to scale, but I probably won't be perfect, right? Imagine that's the same as the other two. Here is my 80. 1 standard deviation, 2 standard deviations, finally 3. Go back 1, go back 2, go back 3. And if you do 3 standard deviations away from the mean, that also has a fixed percentage, which means every distribution in the world that's normal like this, give or take a little, if you go 3 standard deviations either side of the mean, there's a percentage in here. Now, Rachel, you gave the right answer in one of your choices. Can you
Oh, is
now?
it 99.7?
Yes. Where did you get that? You knew one of them was. Where did you
Yeah.
get that from? Is it because you read over the ebook, or you knew it from somewhere else?
I was ahead on the homework. So I tried to finish the homework last night, and so I remembered that.
Okay, so that's physically the number. I like that number, but I'm going to put you, I think this textbook also calls that almost all. That's not a number, it's a phrase. So almost all the data, right? But technically speaking, 99.7. So let's look at these poor people. If you look at that chunk there, that is a range 20 to 40. And the other range is what? 120 to 140. In fact, I guess you could just say anything from 0 to 40 and anything bigger than 120. They would not be considered high. They're like a level above high. They're extremely low and extremely high. In fact, if you do a blood test on someone and something comes up as extremely low and extremely high, they are going to be concerned, right? Because that could be definitely life-threatening. Depends on what, you know, maybe you can live with extremely low iron levels, at least for a relatively long time. You're probably going to be in extreme danger if you've got an extremely low blood pressure or an extremely high blood pressure, aren't you? You know, inches away from taking a heart attack, a coronary, a embolism, or something bad is like. When that happens, they go into you know, as you see in the movies, panic mode, I'll call it, right? Where rush her to the ER, right? Stick things in her, give her fluids, plug it into an ECG, you know, let's figure out what the heck's causing this, because this is life-threatening, right? So can you meet, you've got like a, that's normal, I'm not worried about it, right? Your blood pressure's fine, you know. Okay, it's a bit high, it's probably not going to kill you today, but we want to find out what's causing it. And then, oh dear, we're in trouble. Different things cause these. Since I'm not medical, I'm going to let you share the knowledge. What kind of things give you extremely low blood pressure? The kind of thing that makes you keel over and faint kind of blood pressure, right? Because I think that's what happens when your blood pressure goes really low, you faint a lot, don't you? What kind of things cause that?
Endocrine problems?
I'll take your word for
Dehydration.
it. I don't know. Does that sound right? Endocrine problems?
I think there's also, it's either, I forget if it's too much calcium or is it potassium. It's what they use for lethal injection, but that it will basically stop your heart.
I believe it's
That's-
potassium.
Yeah, that's
Right.
one of the things. Yeah.
Well, that's a bit sad. So
Yeah.
actually, when I picked potassium, I just got lucky because I picked a chemical element at random. So potassium actually is in your body and is something that seems to have a big effect. So if you were low potassium, I mean, a simple cure would be, I guess there's a potassium pill, you know, like you take iron pills and, you know, you just supplement it. Maybe your diet's really bad. Maybe
Bananas
you
are
just,
the best thing for potassium.
that is true. I know that now that you've said that because my wife keeps telling me. You get pins in, this might not be true, but my wife tells me that if you get pins and needles a lot, it's because you're low potassium and you should eat bananas. Is there any truth in that?
I don't know.
I call it pins and needles. I don't know what you call it. Do you know what I mean by pins and needles?
I've
Tingling.
never
Yeah.
heard that one before, but
When I get running cramps, I eat bananas a lot and it helps.
Right. So can you imagine then that you probably won't be extremely low, but you know that would be it. But is anything to do with your heart working badly that might cause that? I mean, if your heart wasn't pumping really well, could that cause extreme high blood pressure, for instance?
If your cardiac output, I think it can affect it. If your cardiac output, there's issues there. I believe that's something that can happen. But I think a lot of it is it's in this Goldilocks range. So if something goes out in your endocrine system, like for example, they were saying endocrine system, that's where you see diseases.
So that's a gland, is it? An endocrine is a gland somewhere?
It's a system, the endocrine system.
It's just a name for the whole process. Okay. So there's different parts of your body regulate the thing.
Right, like you were mentioning, like the testosterone and estrogen that comes from your adrenal glands.
Okay.
So that's an endocrine because anything that's hormones in the blood. So I just took AMP2 this last quarter, so it's fresh in my mind.
So you didn't think when you came in today, the rest of you, that you were going to get a nursing program for 10 minutes? But can you see that this data is helpful? And now you kind of know where they're getting it from. Because basically, all this data is, what's a normal potassium level? Well, do you know what they did is they got literally thousands of people's potassium level. And it ends up being, distributed in some way. And that's how they come in. Now, if you look at that picture that I've got, I'm going to do, the pictures by their nature are going to be a bit ugly, right? Because there's a lot of information in them. But I'm going to try my best to do two different pictures. The first one is just the same guy that we did a minute ago, but I'm going to generalize it. So right in the middle, you've got the mean. And if you go one standard deviation either side, so that's mu plus sigma, and that's mu takeaway sigma. That if you go from there to there, I'm not going to shade it in because there'll be too much shading going on. One standard deviation is 68%. Right. Do you understand what I'm trying to convey in this picture? Right. Now, if you then move out to 2 standard deviations, which takes us to here and to here, then anything between this point here, right, all the way over to this point here, you will find 95% of the data. And then if you finally go 3 standard deviations either side of the mean, I could have planned this a bit better, which is going to be from here basically to here. Would you agree that's virtually everybody? Now, it's sometimes called almost all, at least in this book, and it's also, as a number, 99.7%, which is almost all. And that is my first chart. And I said there's 2. So here is my second chart. I'll try and make it as best I can the same chart. And there is mu, and here is mu plus 1 sigma, here is mu plus 2 sigmas, and here is mu plus 3 sigmas. Mu take away 1 standard deviation, the mean take away 2 standard deviations, and the mean take away 3. Can you pretend that I did that really symmetrically? I know they're not quite balanced, but they should. Now, 34%, 34%. You know from there to there is 68, but isn't from there to there equally split into 2 equal halves? So can you see where the 34 is coming from? So from here to here, I'm going to put the 68% in as well, just as an emphasis. Now, this one you're going to have to trust me, but in this region here, and in this region here, there's 13.5%, and I only mean from here to here, right? So we would call that the region where high potassium level and the region where low potassium level lives. And if you add all these guys together, what number do they all add up to, all 4 of them?
Would it be 95?
Agreed? Yes. And then we got the little baby guy. What colour am I up to? I'm running short of colours. I'll use my pen. In this tiny little area in here, you get 2.35% and 2.35%. Those are meant to be the same shape, by the way. And if you start here and you go all the way to here, won't that be the 99.7%? That's what they add up to, almost all. Now, the reason why this picture is important, and you might want to take a blank version of it and have it beside you for the midterm so it's easy reference, especially for your homework, is that there's a lot of questions that are going to use this. I'll show you how it would work. So I've got this one here. Let me imagine that we did a question where there was a test and the average score was 80 and the standard deviation, well, I'm not telling you it yet, but you're going to be able to tell me what it is. Would you agree in this question, I could have said, what is the mean and standard deviation, only using that picture? Would you agree that the mean is 80? And now I can ask you, what's the standard deviation in this picture?
5.
5. And then you get a bunch of questions that go something like this. They might do it in English, so the first one I'm going to do in English. What percentage of the people in this class got a score between 75 and 85?
Would that be
68%?
68%?
I hear that. I hear 2 people at once and we both agree, which is good. So both of you said 68%. Now, I don't want to draw in this picture because I'm going to use it for lots of things. But if I kind of cover it up, can you see that that is one standard deviation? Basically 34 plus 34, right? The way I do these questions is, think of this as being a cake cut into pieces. And the questions are, you're given this bit of cake. What percentage are you getting, right? So sometimes the cake has 2 pieces in it. You see in this case, it's got 2 pieces and they add up to 68. Can you imagine another question, it might be those 4 pieces. In another question, it might be those 3 pieces and so on. So almost all these questions that you're going to deal with involve you finding what percentage of the data is between this number and that number kind of thing, right? So in this case, the answer would have been 68%. Suppose I asked you to tell me what percentage of the data is in that range. And you see here, I'm not doing it as words, I'm doing it as a little square bracket and interval kind of thing. And that just means between 75 and 80. What percentage of people are there?
34%.
Right, do you see it matches this fella? See how you use this guy as if the numbers were here? So if you said 75, you'd be talking about here, right? If you said 80, you'd be talking about here. Isn't from here to here just one piece of the cake? It's a 34% piece. Now I'm going to write down 3 more. I'm going to keep this guy here, so hopefully that'll help. And you are going to find what percentage are of the data is between these 2 numbers. So what percentage of the data is between 85 and 95? What percentage of the data is between 70 and 85 is my second question. And my third question is, what percentage of the data is between 65 and 85? Okay, you've got 90 seconds, no pressure. Go for it. That's a few things. For me, because I'm a visual person, pieces of cake method work for me, but you may figure out a way of dealing with these questions that makes more sense to you. So 85 to 95, right? Would you agree 85 starts here and 95 finishes there? So that's what I want. Now, isn't that 2 pieces of cake? Now, in my picture, wouldn't 85 be here and 95 be here? So wouldn't it be these 2 pieces of cake? And so that would be made up from a 13.5%, and then you add another 2.35%, and I make that 17.85%. Are we in agreement on that? Because sometimes I can't count.
It should be 15%.
15.8.
Did you all catch that deliberate mistake? Okay. Oh, by the way, did you know that I used to be conceited, but now I'm perfect? Oh, come on, that's a good one. Tomoko, that is a good joke. Yes? Okay. God, it's pitiful when you have to beg for compliments. Come on, that's a good joke. Okay. The next one is 70 to 85. So if I was doing 70, I would guess I would start here and I'd finished here. I'll say it's basically that chunk. What was the final answer? Anybody want to volunteer it?
I got 81.5%.
All right, I have an 81.5. Did anyone else get that?
Yep, I got it too.
Okay, so for those who may not have got it, let's talk it through. Right. So let's talk it through. Basically, I'm looking for 1, 2, 3 pieces of cake. Would you agree it's those 3 pieces? And I'm assuming if you add those up, you get 64, 74. I don't get that. Let me check that again. 70 to 85. Right. So if I do 70, it starts here. And if I do 85, it finishes here. I do not get 81.5. At least I don't think I do. I'll write it down and check. What do I get? I get a piece of cake that's 13.5. I get a 34. I get a 34. It might be I just can't count in my head. So I won't even risk it. A 13.5, add a 64. I get 77.5. Now you want to check that in case I'm wrong. If you start at 70, you're here, right? And if you finish at 85, you're here. Doesn't that mean that it's only those 3 pieces of cake? Now, if I go over to my picture here, isn't it those 3 pieces of cake?
Are you adding 64, 68?
God in Himmel. I'm adding 64. In which case, you
I was
are
gonna
correct.
say, I'm like, wait a minute. I do
Oh,
it all the
God.
time.
I'm just going to sit here and think to myself, you know, you should start thinking about retirement when you can't add 2 34s together. But I have a goal. My goal is to retire when I'm 70. Based on that last mistake, I might have to do it earlier.
It's not you, it's the corona. It's the pandemic. Just blame the
Oh,
pandemic.
good. I've got an excuse. Does that mean I can be a jerk for the rest of the year and I can just blame the pandemic? No? Yeah, I probably shouldn't. My wife, I don't think, will go for that either. Okay. After 3rd time, I still couldn't figure out what I did wrong, but thankfully you stuck to your guns and fixed it for me, which is good news because it means you understood you were right and you went for it. Before I move on, I'll get this out of my head. As you know, this is me in my 40th year of teaching. And some people think that because I've been teaching so long and I've got a couple of degrees and all that good stuff, that if I say 2 + 2 is 5, then I must be correct. It's just some weird arithmetic that you've never seen before and you go for it. No, if I say 2 + 2 is 5, it's because I can't count, right? And you will tell me, should it not be in 68? And I am really okay with that. I truly am. I've got to the stage where I'm really happy when students do that, because what it tells me is that they know what the heck they're doing. They're not just writing down whatever I say, they've actually figured it out and it's right. So that is good news. Right, let's see if I can get the last one right. So we're going to start at 65. Whoa, that's a way over here, right? And we're going to finish at 85, which is a way over here. So isn't that basically going to be 4 pieces of cake? Which I could really say it's just the previous answer add on this little bit. So what you would get when you are finished would be, again, I'm not trusting anything, 81.5 add another 2.35. I hope you got 83.85.
Yes.
Yeah, when you're doing these questions, to me, it becomes, it's always amazing to me how much structure there is in a bell-shaped curve. All I really need to know is tell me the mean and tell me its standard deviation, or at least give me a picture where I can figure it out. And from just that, I can tell you if it's blood pressure, what's a high blood pressure, what's a low blood pressure, what's an extremely high, what's an extremely low, how many people would get a score between this number and that number, right? Could do any of those. And I just thought of one last version of this. I'll call it number 4. And I'll do it in English. What percentage of that class got greater than 85? And you've got to be careful here, because I'm going to use it a slightly different way than you typically would do it. Normally you would add up pieces of cake, right? You'd add up this, and this, right? And that typically is how you do it. But in this case here, that's not a good idea, because technically, if you add up all of those guys, it doesn't add up to 100. So if you add up all those pieces of cake, what percentage does it add up to?
97.7.
That one, right? So if I want to know greater than 85, now greater than 85 basically means everybody over there. And darn it, I've gone and wasted my picture, but never mind, right? Everybody over there. Wouldn't it be a better idea to basically do this in a totally different way? So what I'm going to do is, isn't that half the curve?
Mm-hmm.
Isn't that 50%?
Mm-hmm.
Isn't that piece another 34? Doesn't that add up then to 84? Don't I want 100, take away 84? Won't the answer to that one be 16%? So do you see that the approach I did there was totally different to counting the pieces of cake? Because if I just counted the pieces of cake, I would probably only count those two and not notice that one. There is another way of doing it. I guess, couldn't I find out what that tiny little piece that's left over is, but nobody ever tells you, and do it that way? But in this case here, wasn't it better to get the opposite of what I want to know and take it away from 100? So I found out that this side here was 84, so that I could figure out that was 16. That was kind of the logic behind that. Does that make sense how I approached that last question? Normally you just count cakes.
Can you
Say
do
again?
that again?
Sure.
Okay.
I'll draw another little baby picture of here so I can kind of show you what's going on. Right in the middle at 80, I know how much that is. Are you comfortable? But the left-hand side is half the cake, so it's 50%.
But isn't there still a little maybe extra on the
Well, that little
on the
extra
left?
is counted for in the 50%.
Okay.
If you imagine this shape, if you cut it in half, don't you get 50% of the cake either side?
Yes.
That's what I'm using. Right. Now, this particular one, don't you add in a little bit more, one slice? That gets you to 85, right?
Yes.
Now, altogether, this adds up to 84%. We wanted to know that side, right? So if this is 84, isn't that what's left?
Okay.
Now, if this question had said, what percentage of the people in the class got less than 85, wouldn't the answer this time then be the 84% that we're talking about, right? So on one side it's 84, on the other side it's what's left. So that's a special case, right? Most of the time, adding up pieces of cake works really well, but can you imagine, you know, this is a special situation where you need to adapt. Are we good with this process? Because I want to go and have a look at some of the homework questions on this, just in case there's something I need to talk more about. Are you
Just one more thing. So you round the the left side of the bell curve to 50%.
I didn't even round it to 50. I know it is 50.
Oh, okay. I was adding up the 34.
Yeah, but that
numbers.
only comes to this. So the little piece that's left over here is 0.35% or something, but nobody ever does it that way. Right. Okay. So we are now going to have a look at what does the homework questions look like, and hopefully we can see some examples and they won't be too weird and wonderful. Do I have a homework thing set up? Probably not. Oh, excuse me. Here we are. I'll do a view. I'll go out and I'll go in as we have to. I've been told by a number of people that these videos are not playing. Is that some people? Some do and some don't?
Yeah, mine doesn't. I have Mac. But what I did find is that I just, the title of the video, it says Less Cash and Wallets. I put it into Google and I did find it on YouTube.
Oh God. So somebody's actually had the same problem and went to the trouble of sucking it off the site and doing it for you.
Yeah, I guess this one was like a CNN thing, so it was on there.
Okay, well,
but I don't know if
you get brownie points for initiative. Hmm?
Yeah.
I am going to make sure that I don't put videos on the midterm.
Okay.
Just because I don't want that to be an added stress to you, that you're frantically Googling it to find out what the video is so you can see it. But it's a cool
I'll still be frantic anyways, but you know.
well, that's normal. Okay, now we have 4 shapes here, and they're saying which of any of these curves in the figure below looks like a normal curve. Now, our normal curve has to have a kind of hill shape, but it doesn't always necessarily follow. So I'm going to tell you why it's D, and then first. Do you know that when we draw the curves, isn't that curve just a convenience so I don't have to draw lots of histogram rectangles? Right. So when I draw a curve, it really does mean it's a histogram. We're just superficially curving it to make it easier to draw. And can you imagine if a histogram had hundreds of little skinny rectangles? Wouldn't it look very curve-like anyway, right? So D is equal, it's a single hill, and it's balanced. Agreed? That's a normal curve. It doesn't look like curves. I know the zigzags are an annoyance, but can you imagine if you drew a line through it, it would be a nice, symmetric, single hill situation. So now we're going to talk about why it's not A, B, or C. Let's look at A. A does not count. What is wrong with A?
It's skewed to the left.
Correct. And skewed left ain't allowed. Because can you imagine if you did the little split it in, wouldn't the piece on this side have different cake areas than the piece on the other side? Can you imagine if you went 10, 20, 30, like evenly spaced? Wouldn't one side have a big chunk of cake and the other had a little, hardly any cake at all? In fact, if you did 3 standard deviations either side of this mean, wouldn't you have a couple of guys that don't even have a curve on it? Right, so skewed is out. What's wrong with this one? It doesn't necessarily have a name, but what's wrong with it?
Goes into the negative.
That would work. Would you also agree that it is not symmetric? Right. And you can be not symmetric in lots of ways, but that's only half the battle. Don't you also have to be a single hill, right? A bell shape, or whatever you want to call it. So this shape here is symmetric, agreed? But doesn't this have 3 hills? Or at least it's not bell-shaped. So that's why I'd kick that one in. Now, this is a cool picture because I like pictures where you don't have to do, oh, sorry. let's get the solutions. They distract you, right? Distract me. Okay, back to this fella. Right, from this picture, what is mu equal to?
78.
Nailed it. I'm going to be sneaky here. What's sigma equal to?
Three.
Try again. Sigma?
3.
Nope.
80.
Oh, God.
Would
80.
be 2?
Are you seeing the same picture I'm seeing? I just thought.
Two?
75.
Okay,
Would
before
it be
we.
2?
2.
Right, let's go back to this picture. The
Oh.
answer is 2. All the other numbers, I'm not even sure where 75 came from. Right.
I can't even see them damn little numbers.
Oh, are you using a phone?
No, the screen is just real little. Like you're when you're screen
You can zoom
sharing,
it in.
like it's real.
Tiny? Oh, I didn't realize that. Is that normally when I share a screen, this thing is tiny? Oh, no. So this, for some of you, this is readable, and for others, you can't tell.
Again,
Okay,
sigma is
if you
2.
can't tell, you're probably best just listening to everyone else's answers then, because you won't be able to see it. Do you know
I
that the
can
mean?
zoom my computer screen and I can see it fine.
Okay, so some of you can do it good, and some it's a little bit awkward. Right, can you see that that's 78, then it goes 80, then it goes 82, and then it goes 84? Isn't sigma the standard deviation, the distance between one point and the next? So that's why it's 2. So this guy up at the top here is 78, which represents the mean.
Explanation for it. The other people I know.
And if we do the standard deviation, that's 2. And I kind of kept it fell in the middle to
Eight.
the end. And what number is it? I think I caught it there. Mu
80?
plus
The
80.
80.
Okay. Suppose they had said, what is mu plus 2 sigmas, right? So mu, the little thing that looks like that, plus 2 sigmas. What number would we be at now,
82.
right? And wouldn't 3 sigmas be 84? Right. So they could have, they didn't, but couldn't have put 68, 66, and 64 and did the other side as well, so you got the balance. And that one's pretty much the same question. Now, here's 2 normal distributions. Which one of them has got the biggest standard deviation? I talked about that at the start.
Figure A.
Easy to tell? Right. Aren't you fatter, but not as tall? Fatter, big standard deviation. What I didn't mention, but it's pretty easy to tell you. Do you know that the area of this shape has to be the same size as the area of this shape? And the area of this shape is 1 whole unit, which becomes 100%. So see if you put a little square paper and you did this and you done the height, and you know how you can do that little grid paper and you count the little boxes, you would find that the area of every normal distribution is always going to be 1.
Okay.
And that's turned into 100%. Human beings like 100%. Isn't it better than 0.12? It's better to say 12%. You get a better feel for it. If they asked you for the mean of this one, isn't it 10? And for this one, it's 4. Here's some more pictures, same kind of thing, so I'm not going to do that. Here's our friend. If you have a printer, do you know I'd probably print that picture rather than my hand version, which is a bit cluttersome, right? And you might want to print, you know, a couple of them. That way you can draw all over them when you're doing some of your questions and you know, make a mess, and it won't matter. So they have got what percentage are bigger than this, what percentage are between. Let me pick this one just randomly. In this particular story, the mean is 69, so I'm going to write that down because I'm going to have to leave the screen in a minute. So I'm basically drawing this picture, or at least part of it, and the mean is 69, and the standard deviation is 1.9. And one of the questions they're going to ask us to do is find the percentage between 67.1 and 70.9. And another one of the questions they asked is people who are less than 69 inches tall. Okay, so I'm going to leave this fella. We're going to come back in. And this is kind of how I would be tackling this question. This, for instance, might be what my working would look like in the test. So I would draw a picture like this, and wouldn't I be putting 69 in the middle? And then I would go 1, 2, 3 this side, 1, 2, 3 that side. And in my question, since the standard deviation is 1.9, I would get 70.9, 71, 72.8, and finally 73, 74.7, I believe. And if I went the other side, take 1.9 away, and that's 67.1. You take 1.9 away again. I'm going to have to take my dog out. As you can probably tell, she is telling me it's time for our poo walk. So this guy here is 65.2. I just want to finish this off and then we can do it. And then if I take away one more 1.9, I finish with the 63.3. Okay, why don't I let you do that while I'm gone, and then we come back, we'll check if I'm right. I'll put, oh, where is it? Hold on a second. Here we go. I know it's a bit of a mess, but you know, that's at least something to work with, right? Okay, let's go.
Zoe, he just wants us to find what the percentage between 67.1 and to 70.9.
What did you say?
I was answering Zoe. She wanted to know what he wanted us to find. So, by the way, I think
okay.
it's 60%.
Yeah, 68. That's what I got. I think it's just pretty basic.
Yeah. These are fun. I think they're fun.
I like them too because I'm understanding.
I know, right? I'm understanding that one. I worked a little ahead, and some of them I'm like, okay, it just hurts my brain a little bit, but it's fun once you get used to it.
Did you get 50% for less than 69?
Less than 60? Less than 50?
69.
Oh, less than 69. Oh, it should be 50%.
Yeah.
Because anything less, that's included, like, yeah, half of the cake. I liked his analogy with the cake because I like cake.
My apologies. You know, that never happened when I was teaching in OC. I didn't have to leave to take my dog for a poo walk. My poor wife is not well right now. She would normally do it, but she can't really get out of bed right now. She's not keeping well. And I shouldn't need to do it. You know, we've got a doggy door with a wraparound deck. I mean, she could just go out and do it in the yard because it leads right onto the yard. But she has to do it in her poo place. And I have to take her to her poo place, right? She is a princess. She is spoiled. That's what's wrong with her. And you know that she will bark and bark, and she would do that for the next 2 hours. She gets, to give you an example, 6 o'clock on the dot is her treat time. Every 6 o'clock, right in the day, she gets a treat. And she can't read clocks, but she knows when it's 6 o'clock. So she'll come and she'll whine and she'll bark until you give her her treat, and then she's happy. And if you give her a treat at 5 o'clock, she still barks at 6 because that treat doesn't count. She has a 6 o'clock treat. That's how spoiled she is.
How old is she?
Oh, she is getting old. She's, I think she's 14. She's half deaf, unless you mention food, in which case her hearing is exceptional. And she's going a little bit blind. So she's not very good at jumping up on couches and things. But that doesn't stop her lungs. Her lungs are really good. So we were looking at this question, and I said, you have a shot at it and we'll see how it works. So 67.1 is there. 79.9. Oh, darn it. You got an easy one, didn't you? Agree? What's that? 68%? Oh, God, I've just looked at the next one. Okay, I'm sure that took you 5 minutes. Right. Are you happy about less than 69? Basically means that half of the shape.
Yeah, I have a quick question. Does
Yes.
less than 69 include 69?
Yeah, kind of.
Oh, okay.
Yeah. It gets a bit hard when you say, well, if it doesn't, does 68.999 count? And the answer is yes. So theoretically, doesn't every number count up to that number? So you might as well just use 69. It's a kind of transition point. I'm going to give you one that's not in that list then, because I think we need to do something that involves work. So here is a greater than 67.1, and I'm going to do another less than, and this time I'm going to do less than 65.2, and I'm going to do a 65.2 up to a 70.9. So let's work on these three, because these are a little bit more interesting, right? Because they're not just things you could do without much thinking. So greater than 67.1 would basically be all of that. But remember, when you do, typically when you do a greater than or less than, don't you have a different strategy? So if I wanted to find out what this fella here is, wouldn't I basically say that half is 50%, and that little piece in there, isn't it 34? So actually that one wasn't too bad. That was what, 74%? How about less than 62.5, which is basically going to be this? Wouldn't it be better to find this side and then take away from 100? So what percentage is less than 65.2? Well, let's see what we have. Now, that whole chunk that I'm covering up with my hand is 50. Then you've got this piece, then you've got this piece, right? So if I add up everything going this way, then 100 take away this number. Won't that be the guy I'm really after? So that's the logic of it. So I know this is 50. These two more added onto it, so let's see what that's going to get. It's 100 take away a 50, add it to a 34, add it to a 13.5. And based on my last experience, I probably should do it in the calculator. So it's 100, take away the 50, take away the 34, and finally take away a 13.5. And in this case, I just get, what, 2.5%? So are you comfortable with questions that give you one of these pictures and says, what is the mean and standard deviation? And then they spend the rest of the question asking you for various percentages. What percentage would be between this number and that, like this question here, or greater than this number, or perhaps less than that number? Are we cool? You feel comfortable with that? Right. I'm only doing this as a double check. I just want to make sure that there's nothing in the homework that they may have done that I haven't covered. Classic, they are nice. Look, they give you the picture of each question virtually. Isn't that nice when they do that? Oh, okay. I didn't cover that, although we could probably guess it. So, the mean age of something is 1260. It's an archaeological site. The standard deviation is 37. And they ask you the question in the kind of reverse order. And between what two values do you get 68? Between what two values do you get 95% of the data? And then I think they phrase it as almost all, right? So the last one is almost all. Right, you're going to see my solution right now. Okay, here goes. If you were doing this picture, you do that guy. Wouldn't you go 1 standard deviation, 2 standard deviations, 3 standard deviations, 1, 2, and 3, right? And then you just continue add 37s. So that's 1297. Again, I'll do that in a calculator for safety. 1260, add 37. Right, add another 37. That takes me to 1334. And add another 37. Takes me to 1371. And then subtracting a standard deviation. So 1260, take away a 37. Gets me to here. Take away another 37. Gets me to here. And then taking away one more 37 gets me to here. Now, normally you would create this picture unless the book was nice enough to give it to you, right? And then you would use it to find things like this, right? But not this time. Between what two numbers does 68% of the data lie? Well, in a way, that's a lot easier. Isn't it between there and there? So it's between 1223 and 1297. And when they asked you for 95%, isn't it between here and here? And if they ask you almost all, isn't it between here and here? So that's all that question was, right? 1 standard deviation is 68, 2 gets you 95, 3 gets you almost all. All we're doing is finding out what those numbers are, and we are done. So we're now going to get started on the second section. And in the second section, I'm going to start with a concept called, well, I'll tell you its full name, then I'll tell you what everybody calls it. Its full name is a standardized is a standardized z-score, but everybody just calls it the z-score. The z-score is a number that you get from a piece of data. And what it does is it takes that score and it allows you to compare two different data sets in a fair way. I'll try to explain what a fair way is. First, I'll tell you the calculation, right? That's the mean, right? That's the standard deviation. And X is the data that you are using to get its z-score. So imagine I have two classes. I'll call them class A and I'll call them class B. And they got a term, they got an exam. It was a different exam. In this first class, right, class A, the mean was 70 and the standard deviation was 5. And in this class over here, the mean was a lot lower, it was 50, but the standard deviation was much bigger, right? So in this exam, wasn't there a lot of variation in what the students got? And in this exam, there was a lot less variation. In this exam, wasn't the average score quite poor? In this exam, it was better, right? So here's a problem. There were twin brothers, John and James. And John went to this class. And James went to that class. And John got 60. And so did James, because they're twins and they always do everything the way it's same, right? Which one of those two did, relatively speaking, better than the other? Now, you might say, well, they both got the same score, so they did equally well. But you might say, John got 60 in a test that was quite hard. And James got 60, I should say, in a test that was quite hard. And didn't John do badly in a test that was quite easy? In fact, didn't John get 10 less than the average and didn't James get 10 more than the average? Do you see that they are not equal, right? One of them, relatively speaking, did better than the other. And that's what a z-score allows us to do. It allows us to come up with a number. And the bigger the z-score is, the better you did. And the worse the z-score is, right? And worse means negative numbers, because z-scores are equally positive and negative. Most z-scores actually range between -3 and 3. And you'll discover in a few moments why that magic number happens. So let's do the z-score and see what they got. Well, the z-score is given by x take away mu over sigma. So that's the formula for calculating z-scores. So let's see what John did. Well, John's z-score. Oh, and you know how mathematicians are lazy? We don't even very often write z-score. We just write z. Make sense? If you see z, you know it means z-score, right? That letter of the alphabet is unique. Now, the data is basically 60. Take away the mean, which is 70, divided by the standard deviation is 5. Can you trust me that the answer to that is -2? Make sure you put brackets around your calculator and you'll get the answer. Now, let's see what James did. Well, He's also 60, but isn't his mean 50? And isn't his standard deviation 10? And isn't his z-score 1? So we can quite unequivocally say that James did better, relatively speaking, than John did, because James has got a bigger z-score than John. Are we cool with it? Now, you remember our little guy that looks like this? Let's take this class. 70, 75, 80, and 85, and 65, 60, and 65. This is what you got in the test. Underneath, question, Cody?
The last number should be 55.
What should be 55?
70 to 65 to 60 to 55.
Oh, did I screw up in my counting?
The very first number?
This one?
Left.
60. Oh, yeah.
50.
Yeah, I got it. Thank you. Now, if you take all of these and you find their z-scores, right? Do you know if James had actually got, say, that score, right, 70? Wouldn't his mean, or John, whatever you want to call him, wouldn't his z-score be 70? Take away 70, divide by 5. That ends up being a z-score of 0. In fact, do you know the z-score of the mean will always be 0? Can you see that the way you calculate it, if x is the same number as the mean, won't the top be 0? So a z-score is 0. So someone who got exactly the average in the class, right, Mr. Average, his z-score would be 0 in every case. Now, what about someone who had 75? Now,
Z-score of 1.
yeah, and 2 and 3, and going this way, -1, -2, -3. Do you see that the z-score, if you wanted to say what is a z-score in English, isn't it the number of standard deviations your score is from the mean? So your z-score is how many standard deviations away from the mean you are. Now, z-scores allow you to compare two different groups in what we would consider a fair way, right? A way that doesn't take, you know, just this pure raw data. It takes into account what the distribution of that data looks like, right? What was the mean? What was the standard deviation? Because couldn't that be a really easy test or a really hard test, and you're really not comparing fairly how well each did relative to each other. Try another one. Suppose we had the mean was 30 and the standard deviation was 3. And we'll call that A again. And we call this thing B. And the mean here was 40. And the standard deviation was, say, 10. And I want to compare 50 in both situations. So I guess my question would be, is it harder to get 50 in this quiz, or is it harder to get 50 in this quiz? Well, in one sense that they're equal, but isn't it going to be harder in one test than the other, right? I mean, the means do make a difference, but doesn't the standard deviation also make a difference? Because see, if there's a big variation, isn't it a bit easier to get a high score? But when it's a very small standard deviation, it's quite hard to get a high score. So I'll do the z-scores of each. X, take away mu, divided by the standard deviation. That's going to be 50, take away 30, divided by 3, 20 divided by 3, about 6.7. Well, let's look at the other one. Oh, do you think this one is going to be a bigger Z-score than the other one or a less Z-score? What's your gut feeling? Do you think getting this 50 is going to be harder, in which case the Z-score is going to be bigger than 6.7? Or do you think getting 50? Don't think so? Okay, let's see. There's our formula. $50 take away 40 divided by 10. 10 divided by 10, Z equals 1. That is phenomenally difficult to get, because doesn't that mean you are almost 7, right? You're 6 and a bit standard deviations away from the mean. Doesn't most of the data disappear by the 3rd standard deviation away from the mean? Isn't that virtually everybody? Well, can you imagine going 4, 5, and then 6? That is almost guaranteed to be the highest score anybody got in that test. Right? It's so big, it's ridiculous. Now, this book should do the following, but they didn't. Can you remember when we looked back at outliers? Remember that? And we went and said, there was a rule that went something like, if you took the mean and you added 2.5 standard deviations, remember that test for outliers? If you were 2.5 standard deviations, right? And I said, look, that's not a standard one. It might be an American one, I doubt it. I think it's just this book's one. And do you know what the usual test is? It's 3. And the reason it's 3 is, can you remember, almost all the data is within 3 standard deviations. And do you know if you took a number like that, do you know its Z-score would be 2.5? So if you get a Z-score bigger than 3, you are an outlier. Okay. If you get a Z-score less than -3, you are an outlier. So we can use Z-scores for 2 main purposes. One is, are you an outlier? Is your number a Bill Gates kind of number? And the test should really be bigger than 3, you are. Less than -3, you are not. We are getting some background noise from someone, and I have now muted them, so it should be quiet. So I'd be cool with that idea that Z-scores allow us to tell, are you an outlier or not? And they also allow you to compare things. For my last comparison question, and because that's going to have to be us finished for today, I am going to have a mean of 100 and a standard deviation of 10, and a mean of 90 and a standard deviation of 5. And this person got 125, and this person got 110. Which of those 2 people did better? So which one of those 2 scores would be the hardest to get? This guy in this test, or this guy in this test? Just to show you, you don't need the score to even be the same number to do the comparison. What's your gut feeling? This harder or this harder?
The other one, B.
This one?
Yeah.
Well, let's go for it. Z-score. It's 125, take away 100, divided by 10. 25 divided by 10, that's a 2.5. Do you know that's a really good score, isn't it? You know, in the Z world, isn't that quite a lot of standard deviations away from the mean? You remember 3 is kind of the end of the line typically, isn't that? You're in the top 10% kind of people, right? It's a good score. Let's see if this person is even better. Well, they got 110, which actually is not as good as that. But isn't the mean a lot less and the standard deviation is a lot less? So that could affect it as well, can't it? So let's see how it does affect it. Take away the mean and divide by 5. In this case, you get 20 divided by 5. In this case, you get 4. Not only did this person do relatively better, although this person was good, this guy is great, right? Isn't this person an outlier? You know, it's a bit like you might get this. Have you ever done your chemistry class when everybody's getting 60, 70s and maybe 80 and somebody gets 92? Yeah, you see that 92 person isn't like an outlier, right? Nobody else is even close to him or her, right? That person would have a Z score like 3, 4, 3.1, and then bigger than 3 typically. You would get that. Are we good?
So the further from 0 is better?
I would think so. I want a test. I want bigger than 0, don't you? I want bigger than the mean, right? So yeah. If you do worse, do you know Z scores less than the mean are always negative? You know the way the formula calculates? So a Z score of -3 wouldn't just mean that you did really badly. It meant you did really, really badly, right? You are an outlier. Nobody done anywhere near as bad as you do. You did, right? That kind of bad, right? Like me in a music class, right? If you were grading me on my singing voice, I would be an outlier way down in the -3.5 range, right? If I was a singer, they would use me in a pub and they would only let me sing at closing time so I would help empty the pub. That would be why I would get paid for singing. One very quick thing that just came to me, and I want to do it now in case I forget. Can you imagine you did the data, let's say it was the 91, which is this class here, right? There's the 95, there is the 100, and there is 105. Can you see that his score is way over here in the very rare happening? And can you see visually that that's where the outliers live?
Yes, sir.
Right, and if you go 1, 2, 3 the other way, you go 85, you go 80, you go 75. Can you imagine then that anybody who gets a score in this part of the world, they are also an outlier, but they're an outlier in the sense that they did really badly. Now, sometimes doing best isn't always the biggest Z value. Can you imagine that this represented the number of shots that you took to play golf, right, to finish a game of golf? Funnily enough, in golf, isn't a small score good? You know, if I do a round of golf in 70, that's a good game. If I take 110 shots, that's not a good game. So I don't want us to be too caught up on good means plus and negative Z score mean bad. Most of the time they probably will, but can you imagine there's exceptions to that rule? What's the Z score in 95? I can tell looking at that without doing a calculation.